Hello and welcome to a new video on IGCSE Classified Paper 4 Physics. In this video, we shall be discussing energy, work, and power. First, here we are asked to define power. So power is the rate of energy transfer, or you can define power as the work or energy per unit time. In the following list, take the two boxes next to the two quantities needed to calculate the work done on an object. So the work done on an object is equal to force multiplied by distance, and therefore we're going to choose force and distance. An electric train is initially at rest at a railway station. The motor causes a constant force of 360,000 newtons to act on the train, and the train begins to move. State the form of energy gained by the train as it begins to move. Of course, energy of motion is called kinetic energy. The train travels a distance of 4 kilometers along a straight horizontal track. Calculate the work done on the train during this part of the journey. So like we said before, work is equal to force multiplied by distance. And we are given both the force and the distance, but of course we have to use meters for the distance. So we multiply it by 1,000. So 360,000 multiplied by 1,000 by 4,000, excuse me. That gives us the total work done. And of course, we have to write it in scientific notation. The mass of the train is 450,000 kilograms. Calculate the maximum possible speed of the train at the end of the first 4 kilometers of the journey. So the idea here is to understand that the work done on the train is converted into kinetic energy. So therefore, we equate the work done, which is 1.44 times 10 to the power of 9, to the kinetic energy gained, which is half mv squared. So the next rule you should know is that kinetic energy, EK for kinetic energy, is half mv squared. And the work done results in an increase in kinetic energy. So we equate this expression here to the work done found in part I, and we solve for the velocity. So let me do this here on the right-hand side so that you better understand. We're going to say that work done equals kinetic energy. Work done is 1.44 times 10 to the power of 9. This is equal to the kinetic energy, which is half, times the mass. The mass is 450,000. And multiplied by the velocity squared. So we can simply find v squared by taking everything to the left-hand side. And we get 1.44 times 10 power 9 over 0.5 multiplied by 450,000. So we transferred these numbers to the left. Now we have v squared equals this fraction, and we can calculate v, which turns out to be 80 meters per second. In practice, the speed of the train is much less than the value calculated in I. So just one reason for this. Of course, here we assume that all the work done is transformed into kinetic energy, hence equating these two sides. However, this is not true because some of the work done is lost as heat energy because of friction, because of air resistance, and so on and so forth. After traveling 4 kilometers, the train reaches its maximum speed. It continues at this constant speed on the next section of the track, where the track follows a curve which is part of a circle. State the direction of the resultant force on the train as it follows the curved path. Of course, whenever something is moving in a circle, the resultant force at any point always points towards the center of the circle. And this is called a centripetal force, and it acts towards the center of a circle. So any curved path or circular path has a resultant that is directed towards the center of the circle. Figure 3.1 shows an early water-powered device used to raise a heavy load. The heavy load rests on piston B. Initially, a large weight of water in cylinder A pushes piston A down. This causes the left-hand end of the beam to move down and the right-hand end of the beam to move up. Piston B rises, lifting the heavy load. The weight of water in cylinder A is 80,000 newtons. Calculate the mass of water in cylinder A. Of course, this is quite simple. To get the mass, if you're given the weight, you have to divide by 10. So since this is 80 kilonewtons, so this is 80,000, and then you divide that by 10 and you get 8,000 kilograms. This is how we get the mass of the water. Then we're given the density and required to find the volume. Of course, you should know the rule that says density equals mass divided by volume. So rho equals m over v, or we can rewrite it as v equals m over rho. And in this case, we have the mass as 8,000 divided by the density, which is 1,000, and we get an answer of 8. Question C says piston A moves down a distance of 4 meters. Calculate the gravitational potential energy lost by the water. So the gravitational potential energy, so this is the third rule we're going to learn in this video. Gravitational potential energy is equal to mass times gravity times height. So this is mass, this is gravity, and this is height. Of course, we're given the mass, and we know the value of g, of course, which is 10, and the height is 4, so we multiply them together, and we get the gravitational potential energy. In question D, we are told the heavy load lifted by piston B gains 96 kilojoules of gravitational potential energy. Calculate the efficiency of the device. So the efficiency is output over input times 100. And the output here is 96 kilojoules. The input is 320,000 joules. So this can be rewritten as, if we cross 3 zeros out, this can be rewritten as 320 kilojoules, so that they have the same unit. And then you divide them both by each other and multiply by 100 to get the answer as a percentage. And the answer is 30%. Of course, you could have done it the other way around. You could have written 96 kilojoules as, 96,000 over 320,000, all multiplied by 100. This would not have changed the answer at all. You would have still obtained 30% as the final answer. A coal-fired power station generates electricity at night when it is not needed. Some of this energy is stored by pumping water up to a mountain lake. When there is high demand for electricity, the water is allowed to flow back through turbines to generate electricity. On one occasion, 2.05 times 10 to the power of 8 kilograms of water is pumped up through a vertical height of 500 meters. Calculate the weight of the water. Of course, the weight of the water is simply mass times gravity. So you have the mass, you multiply it by 10. So instead of 2.05 times 10 power 8, you get 2.05 times 10 power 9 newtons. Calculate the gravitational potential energy gained by the water. We already said that the gravitational potential energy is given by mgh. We have the m, we have the g, and we have the h. So we simply plug them in from the given information in the problem. This is the mass, this is the height, and the gravity is 10, of course. And we multiply all of these by each other, and we get 1.03 times 10 to the power of 12 joules. The electrical energy used to pump the water up to the mountain lake is 1.2 times 10 to the power of 12. Only 6.2 times 10 to the power of 11 joules of electrical energy is generated when the water is released. Calculate the efficiency of this energy storage scheme. Of course, this is the output. The output always has to be the smaller value. You'll never get something that has an output greater than the input, because then the efficiency would be more than 100%, and this is not a realistic scenario. So if you're confused about which is out and which is in, the output is always the smaller number. So therefore, we have 6.2 times 10 power 11, which is the smaller number, divided 1.2 times 10 power 12, multiplied by 100, and this gives us an efficiency of 52%. Figure 3.1 shows a cabin used to transport passengers up a hillside. The cabin is attached to a cable which moves horizontally from A to B and then up the hill from B to C. There is an electrical input of energy to the motor which moves the cable. Place 2 ticks against types of energy that increase as the cabin moves horizontally at constant speed from A to B. So this is a bit tricky because you're usually familiar with kinetic energy and gravitational potential energy, so you might want to pick those, but these are incorrect. Horizontally means there is no height. H is 0. There is no increase or decrease in height. So therefore, mgh will always be, so the change in mgh is 0. There is no increase or decrease in gravitational potential energy. As for the speed as well, it's constant. So there is no increase or decrease of kinetic energy, which is half mv squared, which is dependent on speed. So again, this would not work here. So therefore, the correct answers are the internal energy of the surroundings and the internal energy of the wires of the motor. The cabin and passengers have a total mass of 800 kilograms. The vertical distance between B and C is 50. Calculate the increase of gravitational potential energy of the cabin and passengers when they move from B to C. So to get the increase, we simply calculate mgh. We have the mass, which is 800. We have the g, of course, which is 10. And the height is 50. And we plug these in and we find the energy. The cabin then descends back from C to B. The weight of the cabin pulls the cable, which rotates the motor. The electric motor acts as a generator when rotated in this way. Explain the environmental and economic benefits of this arrangement. Of course, this idea of using the weight to generate electricity makes it more sustainable, since in this case, it's creating energy for itself. It's not only consuming energy, so it's generating electricity. So this is a sustainable arrangement economically. And then for the environmental benefits, you're not depending on coal and oil to produce electricity. So therefore, this lesser dependence on other sources of energy, which have harmful environmental effects like acid rain and carbon monoxide. This is, of course, an environmental benefit. A footballer kicks a ball vertically upwards. Initially, the ball is stationary. His boot is in contact with the ball for 0.05 seconds. The average resultant force on the ball during this time is 180 newtons. The ball leaves his foot at 20 meters per second. Calculate the impulse of the force acting on the ball. So this is not strictly related to work energy power, but you're going to see in some of the later questions on this page that we're going to refer to the topic of today. So the impulse of the force acting on the ball is equal to force multiplied by time. We are given the force and we are given the time. There they are. You should focus on the units. So newtons means force, seconds means time, and we multiply them by each other, and this gives us the impulse. Next, we want to find the mass of the ball. So whenever we have impulse and we want to get mass, we start thinking about impulse as the change in momentum. So mv minus mu, where u is the initial speed. Now, initially, the ball is stationary. So that means that it's at rest. The speed is 0. So therefore, this is equal to 0. So I becomes equal to mv. And the impulse is the final momentum, which is 9. So 9 is equal to mv. And we can plug 20 instead of v, since we're given that the speed is 20. And then we can use that to get the mass, 9 divided by 20, which is 0.45. The height to which the ball rises, ignoring air resistance. In order to find the height to which the ball rises, we should understand that this is called the maximum height. And at maximum height, the kinetic energy is 0 because the velocity is 0. So the kinetic energy is 0. So at maximum height, you have the maximum potential energy and you have 0 kinetic energy. So this is equal to the ground level kinetic energy because the ball starts here and reaches maximum height there. So here it has maximum kinetic energy, but the potential energy equals 0. At maximum height, it has 0 kinetic energy, but the potential energy is maximum. So we have maximum potential energy here. So the idea is to equate the maximum potential energy at the maximum height to the maximum kinetic energy as the ball leaves the ground. This is the main idea which we use in order to get the maximum height. So we say mgh equals half mv squared. And v here is on the ground. This is the initial speed, of course, which we already know, which is 20. So 0.5 times 0.45 times 20 squared equals 0.45 times 10 times the height. And we can solve for the h by taking these to the other side. We get 20 meters for the height. While the boot is in contact with the ball is no longer spherical. State the word used to describe the energy stored in the ball. This is called strain energy or elastic potential energy. In this question, we are told that the figure shows a forklift truck lifting a box. The electric motor that drives the lifting mechanism is powered by batteries. The lifting mechanism raises a box of mass 32 kilograms through a vertical distance of 2.5 in 5.4 seconds. Calculate the gravitational potential energy gained by the box. So we said before that gravitational potential energy is mgh, which is 32 for the mass. Gravity is 10. So this is the mass, and gravity, of course, is always 10. And then the distance here is 2.5, and we get 800 joules. The efficiency of the lifting mechanism is 0.65 or 65%. Calculate the input power to the lifting mechanism. So you should know that efficiency is out over in. You can do out over in times 100 if you're going to use percentage. So that's what we did here, out over in times 100. And this is equal to 65. We already know the output. The output is what we got here, which is 800 joules. And we don't know the input, so that's our unknown, our x, for example. So it's as if we're trying to say out over in times 100 equals 65%. So you take this, the 100 to the other side, and then the output here is 800, and we are looking for the input, which is x, and we can cross multiply like this, and you get 800 times 100 equals 65x, and then you divide by 65 in order to get the x, and this is what we get here. This is what we got, 800 times 100 divided by 65. This gives us 1,231 joules. So now that we have the input energy, we want to get the input power. We simply divide that by the given time. The given time is 5.4 seconds. So therefore, we can just divide 1,231 divided by 5.4, and that gives us 227 watts as the input power. The figure shows an aircraft on the deck of an aircraft carrier. The aircraft accelerates from rest along the deck. At takeoff, the aircraft has a speed of 75. The mass of the aircraft is 9,500. Calculate the kinetic energy at takeoff. So the kinetic energy is half mv squared, of course, and we are given the mass and we are given the speed, so there isn't really much to do. We just plug in the mass here and the speed, which is 75. And we get this number after the calculation. So half times 9,500 times 75 squared, which is approximately 2.7 times 10 power 7 joules. On an aircraft carrier, a catapult provides an accelerating force on the aircraft. The catapult provides a constant force for a distance of 150. Calculate the resultant force on the aircraft as it accelerates. Assume that all of the kinetic energy is from the work done. So that tells us that we can equate this kinetic energy value here, which is 2.7 times 10 power 7, to the work done. So now the work, which is force times distance, becomes equal to the value obtained here, which is 2.7 times 10 power 7. So therefore, we can get the force simply by dividing work over distance. So force equals work over distance. And we have the work as 2.7 times 10 power 7. And we have the distance as 150. So we divide and we get the value of the force, which is 1.8 times 10 to the power of 5. A rifle fires a bullet of mass 0.02 kilograms vertically upwards through the air. As it leaves the rifle, the speed of the bullet is 350 meters per second. Calculate the kinetic energy of the bullet as it leaves the rifle. So again, the kinetic energy is half mv squared, and we can simply plug in the values. We're given the v and the m, so we can just plug them into this equation, and we get 1,225 joules, or 1,200 if we're approximating to two significant figures. Next, we want the maximum possible height. Whenever you get maximum possible height, I strongly advise writing this equation here, half mv squared equals mgh, and understanding that this is at takeoff and this is at maximum height. Because at maximum height, there is zero kinetic energy, and at takeoff, there is zero potential energy. So the total is the same. So therefore, you can use this equation to get the value of h. We have m and v and g. So therefore, you can just plug in everything. We already have the kinetic energy as 1,200 or 1,225. So we can just cross this out here and write 1,225. And this is equal to the mass, which is 0.02 times gravity, which is 10 times the height. And this is what we did here. And we obtained the value of h as 6,125 meters. In B, we are told that the actual height is less than the value calculated in A. Of course, the assumption here is that all the kinetic energy is equal to all the potential energy. But in this case, it's not true, because there is air resistance, which causes energy dissipation as heat energy and so on. So there is a loss, in a sense, as the object moves. So therefore, the air resistance exerts a force on the bullet in the opposite direction. So the acceleration decreases. As the bullet rises through the air, its kinetic energy decreases. State what happens to this energy. So it's transformed into two things: gravitational potential energy. But if you only write gravitational potential energy, you will not get the mark. You have to write and heat energy as well. So they're looking here for the fact that some of the kinetic energy is lost as heat energy. A cube of size 0.04 is floating in a container of liquid. The figure shows that the surface of the liquid is 0.028 above the level of the bottom face of the cube. You want to find the pressure at a depth of 0.028. So the pressure due to the liquid at this depth is going to be simply rho gh. We have the density, which is rho, and the density here is equal to 1,500. Gravity is always 10, and the depth is already given. This is h. So we have all the values that we need, and we can calculate the pressure due to the liquid. And then they want the force, and we should know that pressure is also equal to force over area. So if we want to get the force, we take the A to the other side. So F equals P multiplied by A. And we have the pressure and we have the area. So the area of the cube is simply side times side. And we have the side given as 0.04 meters. We just multiply it by itself because this is a square. So we can find the area, and then we use that in order to find the force, which ends up being 0.67. The valve is opened and liquid is pumped into the container. The surface of the liquid rises a distance of 0.034. The cube remains floating in the liquid with its bottom face 0.028 below the surface of the liquid. Calculate the work done on the cube by the force in BII. Again, if you want to find the work, you just use the formula W equals force times distance. you already have the force from before. The force is 0.67, and the distance is given as 0.034. So you have everything you need, and you can simply plug them into the equation. This is the distance here. We have that as well, and we multiply to get the final work. Suggest one reason why this is not an efficient method of lifting up the cube. Well, simply because you're also lifting up the liquid. So if you're lifting up the cube, this method involves energy wasted in lifting up the liquid as well. So this makes it inefficient. If your only target is to lift the cube, then you should not be exerting effort to lift the liquid as well. Figure shows a skier taking part in a downhill race. The mass, the mass of the skier, including his equipment, is 75 kilograms, and the total vertical change in height is 880. Calculate the decrease in gravitational potential energy. So we just have mgh, and we're given the m and the h, and we know g already. So this should be quite straightforward to compute. In B, we are told the skier starts from rest. The total distance traveled during the descent is 2,800, and the average resistive force is 220. You have force and distance, and you're required to find work. Again, this is quite straightforward. You multiply those two values, and you get the value of W as 6.2 times 10 to the power of 5. The kinetic energy of the skier as he crosses the finishing line at the end of the race. So, of course, the work done here is the work done against resistance. So if he has a total energy of 6.6 times 10 power 5, he loses some of that energy in work done against resistance. He actually loses most of that energy, so that the remaining part is only 0.4 times 10 to the power of 5, which is obtained by subtracting these two values, and which is better written as 4 times 10 to the power of 4. This is the kinetic energy he is left with at the end after losing so much energy to resistance. Suggest why the skier bends his body as shown. Of course, to reduce the surface area in contact with air, to reduce the effect of air resistance. Because if he's standing and stretching his arms wide open, he would meet more resistance from air. However, if he curls up his body like this, he's minimizing the contact of the body's surface area with air, and therefore minimizing air resistance. A lift in a high building transports 12 passengers, each of mass 65, through a vertical height of 150 in a time of 64 seconds. Calculate the power needed to transport the passengers through this height. Of course, power is energy over time, so mgh over t. We have the potential energy here as mgh, and this is divided by time. And we are given everything we need. So this is the time here, and we have the 12 is the number of passengers, each of mass 65. So these two together multiplied would give us the mass. If you multiply these two values, you get the total mass. And of course, the height is given as 150 meters. So this is the height here. And we have mgh over t, and we get 18,281 watts, which is roughly equal to 1.8 times 10 to the power of 4 watts. In double I, we're told the lift is driven by an electric motor. State a reason other than friction why the power supplied by the motor is greater than the power needed to transport the passengers, because part of that power is used in transporting the elevator itself. The elevator itself needs power in order to move. So that's part of the energy consumption, and this is not taken into account in our calculations. A soft rubber ball of mass 0.15 is dropped in vacuum from a height of 2 onto a hard surface. The ball then bounces. Calculate the speed with which the ball hits the surface. So this is one of the instances where you equate kinetic and potential energies together. So you write half mv squared equals mgh. You don't really need the mass. You can cross out m, and then you just have half v squared equals gh, and you want to get the v. So you can take the half to the other side. So you get v squared equals 2gh. So therefore, v equals root of 2gh. And you can simply plug in the values here. So it's root of 2 multiplied by 10 multiplied by 2. and that will give you the answer. Let's look at the model answer here. Of course, this is the same as root of 40. And if you get root of 40 on the calculator, you're going to get 6.3, which is the same answer here. So this wraps up this question. We were given the mass, and we could have, by the way, plugged in the mass on both sides. So we could have put in m as 0.15 on the left and on the right. But either way, it would have been unnecessary because they would have canceled out. A spacecraft of mass 35 is traveling in a straight line at a velocity of 1,200. Assume no external forces act on the spacecraft. Calculate the momentum and the kinetic energy. So we have the equations both for momentum and kinetic energy. Momentum is mv, kinetic energy is half mv squared. We are given the mass here, and we are also given the v. The v is 1,200 meters per second. So we plug these values in, and we can get the momentum in question I and the kinetic energy in question II using the same technique. Of course, it's better to write them in scientific notation. So we have 4.2 times 10 to the power of 4, and then 2.5 times 10 to the power of 7 for the kinetic energy. It's a simple matter of writing down the equations and plugging in the values. In C, we are told the rocket fuel stored in the moving spacecraft in B explodes and the spacecraft splits into two sections. One section speeds up and the other section slows down. State what happens to the total momentum. Of course, the total momentum must be conserved. This is a rule in momentum. The total momentum is always conserved. Predict and explain what happens to the total kinetic energy. The total kinetic energy must increase, of course, because this is fuel burning up. So we expect the chemical energy in the fuel to be transformed into kinetic energy. Figure 3.1 shows a waterfall. The speed of the water as it hits the bottom is 21. Calculate the height of the waterfall. So this is similar to one question we just did a couple of questions ago, where we have both kinetic and potential energy. We're given the speed and we want the height. So we simply write mgh equals half mv squared. And again, we cancel out the m's together. We don't care about the m's. And we have g here as 10. And we have the height as an unknown h. And this is equal to half times 21 squared. So we can calculate h by taking the 10 to the other side. So we have h equals half times 21 squared divided by 10. And you can figure this out. Half times 21 squared divided by 10 is equal to 22 meters. State and explain any assumption you made in II. Of course, we assume that there is no air resistance so that the total potential energy would equal the total kinetic energy. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.